So this is the third and final brief lecture on electrochemical impedance spectroscopy. In this lecture, we'll give pointers on two issues. In fact, this is a vast subject. We cannot do justice to these two topics, but you would come across these issues if you're doing experiments. At least I want to give you some pointers where you can go into these topics at much deeper level. So these two topics are impedance associated with mass transport. And sometimes you will see an EAS pattern. You will probably be puzzled. I want to give some pointers for inductance loops that you may see in electrochemical impedance spectroscopy. So let's move on. So the issue at hand is the following. All right. So we have seen this kind of a system where we have a semi-infinite system without any migration and convection. And in a previous lecture, we had looked at when you give a step input, what is the concentration pattern and so on, right? So this is the governing equation. We had analyzed this in some previous lecture. So here we want to look at certain aspects of mass transport and how it affects the EAS pattern. All right, so again, we had seen this also. Supposing we have an AC signal, a small AC signal imposed onto the system, like we have in EAS. If you assume a facile electrochemical reaction, in response to this AC signal, the concentration of the reduced species and oxidized species also show a periodic variation. And again, the current also shows a periodic variation. But what is to be noted is that this time period is the same, but they're all phase shifted. All these variations are phase shifted with respect to the imposed AC signal. So for using these features, that is the features of transport, that is there exists a mass transport boundary layer and these periodic variation, we want to derive certain impedance structures. That is the brief objective of this lecture. So the periodic variation in concentration, this is over and above the steady state that existed before the imposition of the AC signal. This is the variation from this overall variation. Okay, so this is over and above the steady state that existed. Okay, so this is a periodic variation in concentration because of the imposition of the AC signal. So the real part of this signal, this concentration variation, is of this form. Okay, so we have subtracted the mean concentration, and it is just the concentration over and above the mean concentration. So the relevant equation for these systems is this equation in the absence of migration and convection. So if we want to solve this, we take into account this periodic variation and substitute in this equation. This representing these variations in the form of complex numbers has significant advantage, as we have mentioned in the past, in the sense that all the differential operations can be converted to algebraic forms, which makes the solution procedure very easy, right? So we have already used this kind of procedure in the previous lecture. Please refer to that. And in addition, to your textbook, there is a very clear exposition of all these material in this very good book called Electrochemical Impedance Spectroscopy by Lasia. So it's a very good book. So you should probably take a look at this book. If you want to know more details about these derivations and a few other similar system, you can go through this book. It's a very clearly written book. I mean, it's a very specialized book as opposed to Fuller and Harp's book, which covers a lot of material, which is a good book for as a textbook. This is a specialized book on impedance spectroscopy. So a lot of the details are provided in this book. So the relevant boundary conditions are the usual boundary conditions. That is the concentration variation at as x tends to infinity is 0. And then we are going to assume kinetically reversible systems. So the activation barrier for electron transfer is very less. So just knowing the potential variation, we can know the concentration near the electrode surface. This provides us with a significant simplification. Therefore, because this is known, right? This is the AC signal which we impose. The concentration at the electrode surface follows this AC signal because we're just assuming kinetically reversible system. So with that, the relevant boundary conditions and all the necessary conditions for solving this differential equation is available to you. And the current expression for current is given by this equation. Again, we have discussed this in the past. So the impedance for this particular system can be written in this form, right? So, okay, so the solution procedure is also simple given all the boundary conditions. But again, as I said, it is elaborated slightly in your textbook, but much more clearly in this more specialized book. So, but that is not the important feature which I want to point out. So I want to, we want to just address some certain general features of impedance spectra in the context of mass transport. That's where the emphasis is. So substituting all these things in this expression, we can get the impedance, the nature of the impedance for all frequency. What is to be noted is if this particular term, all right, so this may look cryptic, how do we go from here to here, but this is just a review of complex numbers, which you've done in your high school. So you just go through these relationship and substitute it here. Okay, this should be self-evident. All right. So what is most important are these two terms. Okay, so that's what we are going to focus on. So typically, this form of impedance called the Warburg impedance is just due to limitations in mass transport. All right. So, so this is the circuit, relevant circuit, the Randall circuit gets modified by a Warburg impedance, which is in parallel to the Faraday resistance. Okay, so this kind. So when you do an experiment, not in all experiments you will see this Warburg impedance. So unless you have mass transport limitations, you won't really see these issues. So, but sometimes you do see these issues. If you're puzzled, this will tell you why you see the feature. Okay, so how do you know that there is this Warburg impedance? Just before getting into the general feature, your textbook and other books will provide Warburg impedance for a variety of contexts. The expressions become more and more complex, but with a little bit of applied mathematics, all these things can be fairly easily understood, especially for chemical engineering students. Okay, this is just application of things you've learned in transport phenomena in the context of electrochemical engineering. Okay, so even though the expression looks may look daunting, it is not that difficult to derive any of these expressions, especially in the presence of some clearly written textbooks. So, but the issue is the following. Okay, so what you may see is that in addition to these kind of semicircles, you may see a straight line. Okay, angle at 45 degrees. Okay, so that is indicative of Warburg impedance. Not it is not that every EAS spectra which you measure will have this Warburg impedance. Sometimes you do see this feature, the straight line. And the reason for the straight line is that there is mass transfer limitation in your system. Why a straight line angle at 45? That is to do with the magnitude of impedance. So the magnitude of impedance is has this form 1 minus j. So that is the reason why you get 45 degrees centigrade. Okay. The real part, the ratio of the real part and complex part is 1. Okay, that's why you see this 45 degree line. Okay, so for all omega. So that is the take-home message. Okay, is not the mathematical part. The take-home message of this lecture is not the mathematical part. Of course, these mathematical parts can be derived, and it has been derived in other places. But this is the only thing I want to point out is sometimes you may see in your experiment this kind of feature, and the way to rationalize this feature is from mass transfer limitations. So with that, we wrap up that topic and then move on to another topic, which has been elaborated extensively in a recently published book. It's an excellent book by Professor Ramanathan from IIT Madras. This book specializes in reaction mechanism analysis. Okay, I will elaborate in a slide what this is about and why this is very useful, but not adequately explored in the context of electrochemical impedance spectroscopy. Okay, so and one of the advantage with this book written by Ramanathan and Dr. Fatima is that Ramanathan has also given an extensive one semester NPTEL course that that complements the material presented in the book. Okay, so you should go through this book if we are using EAS extensively. So what is, it also goes to other features, more which are all at the cutting edge of electrochemical impedance spectroscopy, like nonlinear electrochemical impedance spectroscopy, which we are not even touching in this course. So it also presents variety of data representation methods like the EAS spectrum, which we have been seeing. This is called the Nyquist plot. There are other ways of presenting the EAS data called Bode plots, which has additional information with respect to phase angle and so on. That is also provided in this very good textbook. And most importantly, both in his NPTEL lectures and in this book, Ramanathan and Dr. Fatima go through when the EAS data is correct. Okay, so it's much of this depends upon linear response theory, and not all data which you get is clean. So the EAS data to be clean, there is something called KKT, Kramer's chronic transformation compliancy. So to understand this, an important thing at least you should be familiar, many times advanced workstations, they do these things for you. They do the work of to see whether the KKT, the impedance spectra you measured is that KKT compliant? Okay, so but at least you should be aware of these kinds of intricacies. It is very well elaborated in this book and in Ramanathan's lecture. So what is this reaction mechanism analysis? Okay, so where is it most useful? So sometimes you may observe, supposing you measure your EA spectrum, you may observe this kind of a spectrum. So what is puzzling about this spectrum is there are these negative resistances. Okay, these are like inductive loops and negative resistances. In fact, Ramanathan's book and NPTEL lectures gives you a zoo of EAS patterns. Okay, you'll be amazed at how complex the EAS pattern may get, even though the electrochemical system that you are looking at it appears to be simple. Okay, that's because EAS is very rich in the kind of physicochemical events it takes into account. Okay, that makes the EAS spectrum very complex. It's information rich. So it's good to know what is the basis for these complexity. So I'll touch a little bit and I'll just mention why is this reaction mechanism analysis very powerful. Okay, so in this system, if you are thinking about inductive loops, so there is no magnetism in the system, there are no magnetic coils and so on. Okay, so there is no reason for you to think through inductance. Okay, so I mean the simple random circuit, we gave a physical basis for ohmic resistances, be it ohmic resistance of the electrolyte or the Faraday resistance involved in electron transfer. We also gave a basis for electrochemical double layer capacitance. Okay, so all these things made sense. Why inductive loop and what's the meaning of these negative resistances? In my opinion, and of course in the opinion of the authors, the electrical circuit analogy, the way of interpreting EAS spectrum just based on electrical circuit is inadequate, especially when you see these negative resistances and inductive loops. To make sense of this, the authors have very well elaborated on a particular way of deriving the EAS spectrum. Okay, so if you just look back, okay, so we derived the EAS spectrum in this system without using electrical circuit. We looked at the concentration variation, and from that you were able to get the impedance spectrum, right? So in a way, physical kinetics is diffusion of physical kinetics, helped you derive the mathematical functional form of the impedance spectrum. Likewise, we can also have chemical kinetics help you get the EAS spectrum. Okay, so what do we mean by that? So if you just fit this spectrum to an electrical circuit, the ideal electrical circuit will have inductance. Okay, so you cannot make sense of inductance in the absence of magnetism. So what you actually do in this book and for many of the system is that you break down your system into different chemical kinetic events. Okay, so this is something which you have done in your chemical reaction engineering class, or in your chemistry students might have done in your chemical kinetics class. Okay, so you have active sites on the surfaces. There are many events like absorption, desorption, dissolution, and of course electron transfer that you elaborate based on these chemical events or chemical events. You can the chemical events are represented in this manner. You can write chemical kinetic equations. Okay, so once you write these chemical kinetic equations, that helps you generate an EAS spectrum. Okay, so in the case of Warburg impedance, we wrote physical kinetic equations and derived the impedance. Okay, in a similar manner, we can write the chemical kinetic equations and derive the EA spectrum. And then those EA spectrums, when you have, let's say, multi-step kinetic mechanism, that helps you rationalize the reason for this negative resistances and inductance. Okay, it has nothing to do with magnetism, just a multi-step reaction. Okay, so this has 3 electron transfer reaction with many intermediates, and the concentration of intermediates, all these issues will help you rationalize the reason for negative impedance and the inductance, okay, without appealing to magnetism. So this is a very important utility of reaction mechanism analysis. Also, it gives you insight, right? Many times we use EAS for electrocatalyst development, okay, not only rationalize the behavior you've seen, but also to rationalize, use EAS for developing new electrocatalysts. For doing that, it is useful to generate the electrochemical impedance spectrum using reaction mechanism analysis. Having said that, it is not easy to derive this for all systems, because once the chemical kinetic mechanism can be complex, it is not so easy to derive this, but it is cutting edge research. Many researchers, including our group, works in this area. So this is an approach that is really worth exploring, especially since there's an extremely good book by Ramanathan and Dr. Fatima. So you should, if you're interested in this reaction mechanism analysis, please take a look at this and the NPTEL lectures of Ramanathan. So with this, we are wrapping up all the material within the scope of this class on electrochemical impedance spectroscopy. So we move to another topic, which is of importance, is the one electroanalytical technique wherein convection plays a role, that is to do with the rotating disk electrode. We'll see that in the next lecture.